Awesome, grow on a plan. शर्मा जी, आप रवि को बोलिए, रवि बिल्गी को चिदम्बरम साहब को फोन करके अगर ट्राई किया है हम चालू करेंगे ना. क्या बोला? एमटीएन का लाइन क्यों गलत कर रहा है? किसको छोड़ो, नहीं होता है, नहीं होता है, क्या करेंगे? तो प्रॉब्लम है ना. ये पूछ क्या यार, क्या है? चालू करना. You can start. I think Dr. Chidambaram is hit the guy. Dr. Chidambaram. मैं अभी पूछ क्या हो यार, अब चालू करना है कि नहीं? ऑफिस से पूछना है, ऑफिस से ही बोला ना. ठीक, तो हम चालू करेंगे. सपोर्ट करें. I can start. Hello, Anurag.
Hello, a very good morning to everybody, and welcome to this very special webinar of HBNI. I would like to, at the outset, welcome Professor J.B. Joshi amongst us. I am very happy that Dr. Anil Kakodkar and Dr. Chidambaram are also joining today's webinar. Professor J.B. Joshi does not require any introduction, but I will be requesting my colleague, Professor P.D. Nayak, to say a few words about Professor Joshi very briefly for the benefit of several of our students and faculty who have joined from different locations, who may not have had the, I should say, opportunity or privilege to interact with him. Well, it is, I must first say that we are very blessed that and privileged that a person like Professor J.B. Joshi is associated with HBNI, and I'm personally privileged that I have known him for more than a decade now and have interacted with him in several platforms. I will not speak about him because Professor Naik will be mentioning about him and his achievements in some detail. But what I want to mention is that when you interact with him, the most important thing that strikes you is his commitment to use science for the benefit of the society and the country, which is seen in every discussion that you have with him. And the second important point, which every student, particularly who interacts with him, will see, his incredible optimism and his conviction about the strength of science and human resource in this country. And anyone who talks to him about the challenge for the society, he will feel that there is nothing which cannot be solved through efforts and through science and technology. That is the kind of confidence that Professor Joshi invokes in every person with whom he interacts. So it's a great privilege to have him as a teacher and as an emeritus professor of the university. And we are indeed very grateful to him for joining today to deliver this lecture. I request Professor P.D. Nayak to give a formal introduction about Professor Joshi, following which we will listen to Professor Joshi. Professor P.D. Nayak.
Good morning and welcome to today's HBNI webinar. I thank Professor Joshi for accepting our invitations to give this very important lectures on prosperity of India through science and technology, opportunities for innovations in entrepreneurship. Yes. Professor Vasudeva Rao already mentioned there is no need of introduction to many of the DE colleagues, but for the benefit of some of our students and those who are not from our R&D unit but from our aided institutes, I will briefly introduce Professor J.B. Joshi. Professor J.B. Joshi is presently an emeritus professor at Homi Bhabha National Institute, HBNI, the former director of Institute of Chemical Technology. At that time, it was known as UDCT, University Department of Chemical Technology, Mumbai. He also was Homi Bhabha Chair Professor at HBNI. In fact, he is one of the well-known chemical engineers in India. He is a consultant and teachers. He has given the consultancy to many industries to improve their chemical processes and other things. Professor Joshi is credited with many innovation designs, especially in the area of multiphase reactors. He developed multiphase parts and mechanically agitated reactors and used it to set up a large number of commercial sized reactors in India and abroad. He has carried out outstanding developmental work. There are many things. Notable among them is the development of new design for household cookers and stoves with thermal efficiency as high as 50 to 60%. The improvement on the conventional cookers, which are normally 12 to 20%. And as Professor Vasudeva already mentioned, he is always for the benefit of the society. So he has released this technology on commercial basis. As an academician, he has published more than 450 scientific papers in peer-reviewed journals with over more than 11,000 citations. He is well-known and respected mentor, teachers, and he has collaborated with many groups of BRC as IGCAR and our chemistry group BRC from which I formally belongs. We have been greatly benefited by his expertise and guidance, how to convert the basic understanding which we have developed through R&D to a technology and make it to a commercial scale. He has successfully guided 69 doctorate theses and 59 master students and supervised 20 postdoctoral students. If you are going through awards, he has many awards. I am not going to mention each and every award. The most important about them is the Santi Swarup Bhatnagar Prize in Engineering Sciences. He also received the third highest civilian honor, Padma Bhushan, in 2014 for his service in the field of chemical engineering and nuclear science. Apart from the academic positions, Professor Joshi has worked on editorial and advisory boards of many well-known and peer-reviewed scientific journals like Chemical Engineering Science Journal, Chemical Engineering Research and Design Journal, Reviews in Chemical Engineering, and there are many more. I feel myself fortunate to come in contact with Professor Joshi. Such a simplicity. Any idea which you have developed in basic science to convert into the technology, I think I have not seen a person better than Professor Joshi. I request all our students of HBNI and maybe other students who may be listening to this talk, as well as young faculty, if they feel that basic science, what they have developed, have some chances to get converted into technology, but they don't know how to convert it, I think Professor Joshi is the best person. It may be in chemical science, it may be in any other discipline, maybe physics, maybe in biology. But I'm quite sure you'll able to guide each and everybody how to convert whatever knowledge gained through basic research to a technological aspects for it. In fact, if our students like to have the one-to-one interactions with Professor Joshi, we can arrange the interaction session some other time. For the benefits of our students and young faculty, his Gmail ID is jbjoshi@gmail.com. And I think you'll not mind, I'll take kind permission from Professor Joshi. If you really feel that your basic ideas, some chances to convert into the technology, I think you should come in contact with him. And I'm quite sure he'll be ready to help you. And after your interaction with him, I think you'll be greatly benefited and you'll be become a friend of him because he is so simple person. He can mix with any group age. That is, if you are just 20, 21, or maybe in 50, or maybe in your 80, he has that mixing capability. He is socially very active and he can mix with anybody. And I'm sure that our students of HBNI especially will take benefit of his expertise and his experiences he have for last many years. Professor Joshi, please.
Hello.
You can with questions. You can continue. Start from beginning. Beginning. Just give 1 minute.
Yeah. First of all, many thanks to Honorable Vice Chancellor Professor Vasudeva and Dean Professor P.D. Naik for giving me this opportunity. I'm aware that uh, in the audience we have respected Dr. Kakodkar and respected Dr. Chidambaram and many other distinguished faculty and scientists and also my dear friends. First of all, I express my gratitude to Department of Atomic Energy in general and HBNI in particular. I have been physically here in HBNI for 11 years, but prior to that 35 years, I have been connected with atomic energy. I feel that working in atomic energy is a paradise, mainly because whatever facilities you wish to have, that facility is there, and whatever expertise you would like to interact, all those expertise are also existing in atomic energy. So I have been interacting with several groups, that is reactor engineering, chemical technology, chemistry, materials, and beam technology, as well as several groups in IGCAR. I have supervised more than 100 students, published more than 200 papers in these 11 years, and it has been thoroughly enjoyable experience. Today, I'm talking about prosperity of India through science and technology. And it has been decided that I will give this lecture in two parts. Part one is wealth generation, that is prosperity of India through university industry partnership. Whereas in the second part, I will be covering the opportunities of entrepreneurship and relationship with the society. Actually, there is a one concept called sealage, which is pioneered and mission has been taken by Dr. Kakodkar, and I'm one of the worker in that mission, that is the prosperity of our Indian society through science and technology through sealage. So the subject of sealage I will be covering in part two, and that announcement will be made later. Today I will mainly cover the prosperity of India through university industry partnership. Now, if we look at the mission statements, of variety of universities in the world, take for example, University of Cambridge. That statement is large. I will request you to focus on the words which are read. So University of Cambridge is to contribute to society through the pursuit of education, learning, and research at the highest international level of excellence. Please note, contribute to society is there, and fundamental education the second part. So let me start with first part. Whenever we say that the university wishes to serve society, develop technologies for the society, or disseminate knowledge to the society, so that becomes the first component. I would like to bring to your attention that more than 50% of innovations, they happen in the university atmosphere. This is a worldwide survey which has been taken, because the students in the university and faculty members in the university, they don't look at the watch. They work for 70 hours, 80 hours. Then all the mission statements, I'm stating this again, there has to be a balanced approach between fundamental science, the engineering science, the innovations, and implementations. So if this is the summary, and if you want to serve industry and society and generally participate in the prosperity of our nation, then what is the biggest problem faced by our nation? And quickly it will come to our mind that though our nation is called developing nation, it is really one of the poor nations. And solving the problem of nation means how to work at the prosperity of our nation. That is the biggest problem of our nation, and it becomes a responsibility of all the universities to generation of wealth which can be useful for a common man. I'm going to elaborate this particular sentence in great detail in my remaining lecture. What do we mean by our nation is poor? So if we go to the next slide, here I have made a list of several nations in the second column, and first column is ranking of these nations on the basis of per capita income. That is the ranking, and actual per capita income is in the third column, and innovation ranking is in the last column. And you can see that India is 140th from the top, or if there are 180 nations, then it is 40th from the bottom. And the per capita income is about $1,700 per year per person, which is about 1 lakh rupees. And our innovation index is also 81. There are changes in the GDP ranking and innovation ranking year after year. Some changes may occur, but if you make a plot of innovation ranking with GDP ranking, you can see that there is almost a straight line. So those who innovate, the nations in which the scientists and engineers, they innovate and develop new attractive technologies, either for products or for services, or they develop some innovative processes and technologies and do business throughout the world, and in this manner collect wealth for the nation. Those are the developed nations. So this relationship I want to bring to the attention of all, that the innovation ranking and GDP ranking, these are strongly correlated. So what it means is, if you want to generate wealth for our nation, if you want to make our nation prosperous, what is required is we should go ahead in terms of number of innovations per person per year. So I have already said our number in terms of per capita income is 140th from the top. So why it is so? The income of the nation mainly comes from three resources. One is industrial resource, second is agricultural, and third is the service sector. And if we take these three resources together, it forms, depending upon the nation, between 65 to 90% of the income of that nation. Now, if we consider our nation, and take the industrial activity, and since I'm closer to the chemical industry, I'm giving some numbers. The turnover of chemical industry throughout the world is 14 million crores. 14 million crores. Whereas the turnover of Indian industry is 2 lakh crores. So we do business in the international market only 2 lakh crores. Or our participation in the worldwide market is about 1.4%. If we take the another sector, that is herbal healthcare, and here we proudly say that this is the science which has been originated in India. But what is our participation in the business? The 15 lakh crores is the business available in the world, but India does business only 15,000. That is 1%. Food processing, 1.5%. In electronics, let it be mobile or TVs or many advanced gadgets, our participation is 0.1%. Mechanical engineering, 1.2%. Biotechnology, 0.9%. Energy is 4%. But if you take majority of the sectors, our participation in the world market, in the world turnover, is 1% plus minus 0.5%. The next slide shows the productivity of different crops in our nation. And I have listed some crops in the second column, like rice, wheat, mangoes, sugarcane, etc. And what is the productivity per hectare is shown in the third column, and what is the possible productivity in the world is shown in the fourth column. So if you see any crop, rice, the per hectare productivity is 3.3 tons in India. What is proven in the world is 10.8 tons per hectare. Take any other, cotton, 1.6 tons, 4.6 tons. So the Indian productivity is about 1/3. Take, for example, tomatoes. Tomatoes, in that case, our productivity is almost 20 to 25 times less. Why this has happened? Mainly because the fertility of our land has gone down year after year because of several reasons. And I'm going to elaborate on this in my second part, how to make our land fertile from the existing unfertile land. If we take service sector, we are doing much better in service sector, but as far as any original software is concerned, which has the international market and has a good value, and it can form a good resource for our nation, such softwares have not been developed by our service sector. They are only giving services to other nations. They get dollars and they give good salary to our engineers. But it doesn't add much to the income of our nation. So if you take industry, agricultural and service sector, all put together, the total income is 140 lakh crores. Our population is about 140 crores. So income divided by population, therefore per capita income is 1 lakh, 140th from the top, and our nation is poor. Now this part I'm going to repeat again and again because that is the objective of this lecture, how to make our nation prosperous and raise from 140. We will focus on how to increase the wealth for our nation by means of many innovations. While we are poor as a nation, resources wise, we are very good. We have excellent resources. For instance, take the metal titanium. Total reserves in the world are 600 million tons, in which the reserves in India are about 100 million tons. It's a good quantity. And when there was a tsunami in about 2008, we know that several bad effects caused by tsunami, but one good effect, positively good effect is the sand, which contains about 50% titanium. Lot more sand was deposited in our East Coast. And how much sand we have? If we have the technology for titanium, then we can supply to the total world for next 500 years. That much we are having. But we don't have innovation, we don't have technology. So what is the current practice? We are exporting the ore at 6 rupees a kilogram, and we definitely need to import titanium because it is a strategic material at 2,500 rupees per kg. Please note that in the raw material, the titanium is 50%, and we are selling at 6 rupees a kilogram. And there are, I can give you several examples where we have plenty opportunities, particularly in medicinal plants and many others, in pulses also. But the important point is the number of innovations happening, they need to accelerate to catch the value in terms of wealth for our nation. Again, since we are poor, still we need to import plenty things. Crude oil, 12 lakh crores. Electronic equipment, 2 lakh crores. And I have listed only 10, and a big list is available for in the internet for everybody. There are hundreds of items which we are importing from outside. Actually, you may remember that during last 3-4 years, our nation has been visited by Canadian Prime Minister, Chancellor of Germany, then Prime Minister of South Africa, Prime Minister of Australia, head of China. All of them visited. And among many other things, they definitely signed MOU with our nation for selling products which have been innovated in their nations. And we are importing. The most important critical part, and if you see in the internet, which nation is importing maximum the equipment, the machinery related to defense. And you will quickly get that India is the maximum importer as far as defense is concerned. Now, I'll tell you what is the most important point which really is at the top of my mind. If you take any defense item and if you are importing, and even if you have lot of money, and atomic energy is very familiar with this, that is, that particular nation says you pay us any amount of money and we are not going to sell you the defense equipment. And then you see the security of our nation. So this is a frightful situation where the absence of innovations are compelling us to import from outside at prices which are sometimes 3 times, 5 times, 10 times higher than the actual possible price if innovation was done in India. That is one part of it, but it is affecting the security of our nation. Now, we are clear that why per capita income is less, mainly because of the resources from industry, from agriculture, and from service industry. Those are limited. And the reason for that is number of innovations are less. But if I had done a survey among our industry, our academia, and among common citizens, what are the reasons that we are not innovating? Why our nation is poor? And what is that we can participate? And I will share with you only some points. I met various industrialists, that is, why we do not participate, say 10% or 20% in the worldwide market. So what do they say? Let me emphasize here that this slide is most important out of all the slides. So even if internet stops and electricity stops now, and if I am able to explain this slide, I'll feel very happy that I have been able to explain whatever I wanted to say. What is that industry says? Why we are not competitive in the world? because our nation provides poor infrastructure in terms of roads and railways and communications and the ease of doing the business. Whatever is infrastructure required, it takes months and years to get permissions. Then cost of finance is high. That is, if you want to raise capital for starting business, the interest is in the range of 12%, 13%. Whereas in USA it is 5%, in Switzerland it is 2 to 3%, and in Middle East there is no interest. The cost of energy, we need to pay about 8 to 10 rupees per unit in India. In United States it is 4 to 5 rupees. In Switzerland it is 1 or 2 rupees, and in Middle East it is free. So if cost of finance and cost of energy is high, then how our business can be competitive? I'm going to show later on that if we have the right innovations, then the cost of finance and cost of energy is really negligible. So whatever the reasons, I call these as excuses. If you don't innovate and if you are not competitive, then there is always a list of excuses. So poor infrastructure, cost of finance, cost of energy, whatever are the costs of energy, I'm going to give several examples that the cost of energy is negligible. So there is no incentive for R&D which our government gives. And most important complaint that industry makes, we do not get meaningful help from academic institutions and R&D institutions. That is the main complaint that they have. If we go to academia and universities, what is that they wish to say? We get bigger funding from governments. Then these days, there is a poor availability of good students. Now, I have been faculty in the university for almost 50 years, and this is being said for all the 50 years, that these days we don't get good students. And when we complain that there is poor availability of good students, then the students have a right to say that these days there is a poor availability of good teachers. Now, if we wish to have excuses for our non-performance, the list can be very big, from academia, from industry, and from a common man. But the most important complaint that academicians give, that we do not get meaningful support from industry. On one side, industry says we do not get meaningful support from academic institutions. Academics say that we don't get meaningful support from industry. If we innovate something and go to industry, they give nice lunch, they respect, but they don't take our technology. So we have to file the technology because of non-cooperation from industry. So these are the complaints. The common citizen, our nation is poor mainly because of our politicians. If the politicians are cleaner than today, then we would have been much better. But I'm telling you honestly that I was head of my department of Chemical Technology, UDCT, and during my period, I converted into autonomous institution, and I became dean of my institution with the same table and same chair, and I converted the same institute to full-fledged university, and I became vice chancellor. And during this period, I had to meet many, many politicians, including the center and state. And I'm again telling you honestly that the understanding of the education was much better than the vice chancellors then. They were so much committed themselves, and the depth of their understanding was very good. So we cannot make a swapping statement that our nation is poor mainly because of politicians. The main difficulty is we have a habit of making complaints. So those who are students in the audience, my dear students, please listen to me. Those who complain in life, they cannot do anything meaningful in life. You keep on smiling, you will do something. So after reading this slide and having listened to the explanation about this slide, one important thing we should remember that giving excuses and making complaints in life, we should leave it as soon as possible. And then we should start smiling and creating positivity in the society and our peer group. And then immediately innovations will start. I'm going to tell you the university industry partnership that I have been able to enjoy while I was faculty for about 38 years in Institute of Chemical Technology. Please note that when I retired as a head of the institution, at that time, 80% of our expenditure was coming from the research projects and donations, 80%, whereas 20% was from government. Ours is an aided institution. It is not a private institution. And I'm telling you this number 80% is a conservative number. So how we develop that kind of culture in the institution, I'm going to elaborate in a little bit detail. That is how many innovations and technologies were developed in India and how the wealth which was going to other nations, that was not only stopped, but wealth generation started happening in our own nation. I'm going to give you a few examples. The first example is self-inducing reactors. There are various chemical reactions where hydrogenation is required. And till about mid-80s, the hydrogenation was being done by taking iron filings in the vessel, and whatever to be hydrogenated, there are many cases where hydrogenation is required. The conversion of nitro group to amino group, the saturation of double bond, then conversion of cyanide group CN to CH2NH2, then the saturation of the aromatic ring. There are many, many examples. But whatever is to be hydrogenated, say simple example, nitrobenzene, then take in the vessel iron filings and nitrobenzene and add hydrochloric acid to this vessel. So what will happen? Iron would react with HCl to give FeCl2 and hydrogen. And this nascent hydrogen would react with nitrobenzene and we get aniline. What were the problems with this? First of all, it was very unclean process. When we used to get about 1 kilo product, then 3 kilos of solid waste was getting formed. And this solid waste was entraining about 5 to 10% of the main product. So 10% profit was eaten away by the waste itself. And we know that all the amino compounds are carcinogenic, and therefore disposal of this solid waste was a big problem. So anyway, catalytic hydrogenation was known at that time, and this process was not very good. But the catalytic hydrogenation, whatever were the reactors available then in India, like say for example, which is shown here, a stir tank. It is a bigger version of a mixer in our household. There is an impeller which does several jobs. In the household, there are certain jobs of mixing and homogenization. In industry, there are many other jobs, and some of those jobs I'm going to explain. So here, in the presence of catalyst, the hydrogen is passed below the impeller. The gas phase is converted into bubbles, and bubbles are distributed throughout the equipment by the impeller action. Since the solubility of hydrogen is pretty low, most of the hydrogen goes to the gas space without any reaction. And we cannot let out this hydrogen because hydrogen is very expensive. If it is made electrically by electrolysis, and present cost is 8 rupees per unit, and 65 units are required per kilogram of hydrogen, it is more than 400 rupees as a raw material cost. If you add several expenses, it will be 650 rupees. So that hydrogen has to be utilized. So whatever was the known knowledge then, first of all, it used to take several days for catalytic hydrogenation, 4 days, 5 days, and hydrogen was being lost. One simple way to recycle hydrogen was external compressor, but it was not a safe way. Any external recycle of hydrogen is not a good idea, and compressor is a expensive equipment. So what is required is whatever fresh hydrogen is passed and unreacted hydrogen goes to gas phase, it has to be recycled into the liquid phase again. But whatever goes to gas phase, it cannot enter the liquid because of the static pressure, H rho G, and it cannot travel, the gas cannot travel against H rho G. Therefore, what is the innovation? Innovation required. Now the impeller is surrounded by hood and shaft is surrounded by an annular pipe. And if you can see that there is an opening in the gas space, and whenever impeller rotates, we know the Bernoulli's principle that the sum of the mechanical energies like kinetic energy, the potential energy, and the pressure energy, the sum is always equal. So when the impeller starts rotating, we enhance the kinetic energy, and pressure in the vicinity of impeller, it goes down. And if that pressure in the absence of any rotation is H rho G, that is H is the liquid height above the impeller, rho into G. Now, if the reduction in the pressure because of the impeller movement and local increase in velocity of liquid is in such a way that local pressure is less than gas phase pressure, then the gas, unreacted gas in the gas phase will enter through the gas entrance and it will flow through the space available between the shaft and the annular space, and then it will go to impeller region, which is further broken by the impeller, and it is available for dispersion. Now, such a reactor design was known in the world, and therefore one of the industrialists, he requested me to get an imported equipment from outside, and therefore such a technology was available in Switzerland, and therefore I went to Switzerland and asked the cost for 2-ton capacity reactor, and the quotation was 10 crores. Now I quickly realized that 2-ton reactor for which the metal requirement is not more than 15 lakhs and the quotation is 15 crores. I'm giving these examples again and again why our nation is poor. We don't have our local technology. So the 10 crore machinery, if we come back and take a loan from a bank for 10 crores, and there is a depreciation, there is an interest, and there are costs associated to 10 crores, and these costs, when these are factored into the cost of the product, say for example paracetamol is made by catalytic hydrogenation, then we will not be competitive if we are importing technology. Please note that we have about 18 refineries in India. If you wish to have 19th refinery, we buy total technology import from outside. We have 75 fertilizer plants. If you wish to have another fertilizer plant, again we bring technology from outside. And how much we are paying from outside? I'm giving you the same example. Since the price was 10 crores for the catalytic hydrogenation reactor, I came back and I told the industrialist that this is not tenable. Let us not buy this reactor from this company. But the industrialist friend was wise. What he told me was, you go again, our fabrication facility in India is very good. Anyway, raw material required is only 15 lakh rupees. If we pay another maybe 10 lakh, 15 lakh, we will get it fabricated. let us get only drawing from outside. So I went back to Switzerland, and it was a heavy winter, and I asked the cost of drawings. First of all, they were very ready to supply the drawing. The cost of the total equipment is 10 crores. The cost of the drawing is 9 crores 70 lakhs. And in the remaining 30 lakh, whatever you want to save, you save. So please remember, then since it was winter, my blood started boiling in Switzerland winter. That the India is taking for granted that the cost of production, wherever it is 35 lakh of rupees, we are importing equipment at 10 crores. And this is happening again and again. I gave you several examples of titanium and plenty equipment which you are importing from outside. So when I came back with the help of the institutions in the university, in about 3-year period, this equipment was innovated. Here you can see the impeller is located towards the top, and the gas which is dispersed into bubbles, there is a lot of empty space at the bottom which is not participating in the reaction. Therefore, if you bring the impeller down, then gas liquid dispersion is throughout the vessel. However, the resistance which the induction has to overcome, that H rho G is high, and therefore rate of induction is low. So what we had to innovate was keep the inducing impeller at the top and designing the dispersing impeller which disperses the gas which is induced by the gas inducing impeller. Here I will tell you the connectivity between fundamental science, the understanding of fluid mechanics, and its role on the reactor design. I have already explained to you that in the impeller region, the pressure has to be lower than the pressure in the gas space. Then only self-induction will start. So we need to analyze the fluid mechanics in the vicinity of impeller, and we did it with the help of computational fluid dynamics and tried to understand the local flow pattern, local pressure pattern, and for a given power consumption, which impeller design can give the lowest pressure and highest rate of induction. Similarly, for dispersing impeller, again we had to understand the flow pattern so that that impeller becomes efficient as far as dispersion of gas is concerned. But it is known that the impeller which is most efficient for dispersing is not good for catalyst suspension. It is a 3-phase reactor, gas, liquid, solid, and solid is a catalyst. So we had to design the third impeller where the requirement was the fluid mechanics generated by that impeller should efficiently suspend the catalyst. After understanding and innovating these 3 impellers, we could fabricate the same reactor in 30 lakh rupees. So in 1991, the first reactor was implemented. Now please note that whatever can be fabricated in India in 30 lakh rupees, who is going to buy from outside? Now, whenever it was quoted 10 crores, the dollar price was 10 rupees. So it was almost 1 crore per reactor, 1 crore dollars. Then the price of the rupee became 20 rupees and 30 rupees. And since the import stopped, the company reduced the price from 10 crores to 5 crores to 2 crores, and the exchange price exceeded. But then also there was no import. And then we, as an institution, implemented this for 150 different hydrogenation technologies in India with a turnover, huge turnover. And where we were importers, now 50% of the production we started exporting, and where we were participating only 1% throughout the market, worldwide market, these hydrogenated products, we could export more than 10%. Now, how many benefits are there if we innovate in the university and develop excellent partnership with industry. The first benefit, industry sponsors. And whenever industry sponsors, there are two benefits. They expand their activities and therefore job opportunities increase. So there is first win that industry sponsors. There are many more job opportunities, second win. Whenever there are bigger profits by industry, there are taxes which are collected by the nation, that is the third win. If the university is able to innovate, then we get projects, research projects. That is the fourth win, that the institute starts getting the projects from outside. The teacher who is responsible, he gets the royalty. Then the students get fellowship. So there is a win-win-win-win-win-win situation if there are innovations which are happening in the university. Now, in the same line, I'm going to give you 2-3 more examples. We innovated a new reactor for hydrogen peroxide. How hydrogen peroxide is manufactured? We start from ethyl naphthalene and we hydrogenate it catalytically, but we need to hydrogenate only one ring. And that hydrogenated ring, it is oxidized, and we get hydrogen peroxide, and we get back the raw material, ethyl naphthalene. But if we over-hydrogenate and both the rings are hydrogenated as shown, then that is a solid product. And if solid product is made in a continuous process, then there is a discontinuity in the operation. The solids, they choke the reactor, they choke the transfer lines, and we had to stop. When this problem had come to university, then we first of all understood the mechanism and kinetics of this reaction. The mechanism was, the first ring hydrogenation is hydrogen mass transfer controlled, whereas second hydrogenation was completely reaction controlled. So the answer to this process was, if we keep it mass transfer controlled, then there will not be any dissolved hydrogen and the second reaction will not stop. So when this problem had come to our institution, it was 70% conversion and 70% yield. And when we controlled mass transfer with chemical reaction, the yield and selectivity improved from 70% to 80% and then 90% to 100%. And when there is a excellent collaboration with industry, the industry people also intelligently participate. So from 70% conversion, they went to 80% conversion, 100% selectivity, 90% conversion, 100% selectivity, 100% conversion, 100% selectivity. I mentioned to you earlier, these win-win-win-win situations, these are useful to the university. And 80% of the expenditure of my institution started coming from such research projects. Where we were spending money? Anyway, the salaries of the teaching staff and non-teaching staff, 80% of the salary was supported by the government. So we had to support 20% salaries. All the library expenditure, all the expenditure of utilities, electricity, water, etc., that we had to bear. But most importantly, more than 400 PhD students, it was our desire. It was not government's desire that you shall take the PhD students, but it was our desire. We were taking 400 students. So their fellowship and their expenditure was the major expenditure, but which we were lacking, and therefore we were collecting 80% of our expenditure from outside. We did a lot of construction because increased PhD activities means increased lab space. We wanted more than 3 lakh square feet. We wanted student hostels. We wanted faculty houses. And we never went to government because there were innovations and industry was getting benefited. We appealed to industry that you support one floor for either hostel or faculty house or for for the laboratory, and we could construct large spaces in the institution. So I'm giving you this example. What was the innovation in hydrogen peroxide? Now here you see a bubble column reactor, which is a vertical cylindrical vessel, and there are catalyst particles. You see the filled dots, which is catalyst particles, and the gas phase is the hydrogen. So hydrogen is passed at the bottom. Catalyst, in the absence of hydrogen flow, it sits at the bottom. Whenever bubbles flow, there is a turbulence generated by the bubbles, and this turbulence so generated, it creates dispersion in the liquid phase, and that dispersion starts suspending the solid particles. Here also the hydrogen solubility in ethyl naphthalene is poor, so it goes at the top, and the compressor does the job of recirculating. Now when this problem had come to us, there was a certain volume of the reactor, or for a given volume there was a certain capacity, and the compressor was of 150 kilowatts. Why that compressor was high? Because as you see, the catalyst concentration is very high at the bottom, and it exponentially decreases from bottom to top. And the catalyst suspension decided the efficiency of the reactor. If we improve the catalyst suspension through the gas velocity, then what will happen? Then there is an increase in mass transfer from gas phase to liquid phase. There will be finite concentration of hydrogen, and further hydrogenation of the second ring would happen, and that was the major problem of industry. So without hydrogenating second ring, by keeping it mass transfer control, how to do this operation. So the catalyst suspension by gas phase, this was to be decoupled, because this coupling was really the severe problem. So what was done was, as you see, there is a parallel pipe to the reactor, which is connected at the top, and it is connected at the bottom as well. And in the main reactor, there is a gas liquid solid dispersion, and in the downcomer pipe, in the parallel pipe, there is only solid and liquid mixture. So the mixture density of solid and liquid is much higher than the density of gas liquid solid in the main reactor, because gas doesn't participate in the density because hydrogen density is negligible. So if you see similar locations at the bottom horizontally, bottom of the downcomer and bottom of the reactor H rho g is less than H rho g in the parallel pipe. So a pressure driving force is gets generated, and the flow starts in the horizontal pipe to the reactor bottom, and then vertically upwards. Then it will take a turn, and then it will come to the downcomer. Now this upflow, which entirely depends upon the difference in pressure in the reactor, in the downcomer, we can keep upward velocity in such a way that catalyst gets suspended. Now the job of gas phase for catalyst suspension, that job was removed from the gas phase, and that job was given to the upward liquid motion, and the catalyst suspension would occur. Now the gas velocity required is not high, and the gas velocity was controlled to a number in such a way that the mass transfer coefficient is so low that it remains mass transfer controlled. Hydrogen solubility is poor, and then the second reaction will not happen. So, and therefore the selectivity improved from 70% to 80% to 100%. Again, industry sponsored many other projects because they prospered, and therefore they sponsored research project to the institution. I'm giving you yet another example. This is a very heavy raw material, heavy in terms of consumption. It is a raw material for polyester. It is terphthalic acid. You know that a polymer of terthalic acid and monoethylene glycol is a polyester. And the starting raw material is paraxylene, and it oxidizes in steps, and finally, eventually, we get terthalic acid. This oxidation is a radical mechanism. And whenever there is a radicals are formed of paraxylene, there is a possibility of two radicals joining together, and dimer would form, tetramer would form, and polymer would form instead of further oxidation. And there was the real complaint from industry was the final product, terthalic acid, was sometimes yellow, sometimes brown, and sometimes black. And it entirely, whenever we understood this mechanism, that it was basically because of radical polymerization. If the polymerization is at low level, then we will get yellow color. Further polymerization will give brown color. Further polymerization would give black color. And if we stop this radical mechanism by having sufficient oxygen as the dissolved oxygen, then polymerization could stop. So this was understood in 1 liter reactor. So it was important that in the large scale, we manage the desired value of dissolved oxygen so that the problem of quality would stop. One important point I want to bring to your attention, that this oxidation is carried out with co-solvent, that is acetic acid. That is acetic acid and paraxylene in the ratio of 4:1 is added to the reactor, and it is brought in contact with oxygen from air. So whenever paraxylene oxidizes, acetic acid also oxidizes. So when we started this problem, 100 kgs of acetic acid would react, would consume, will oxidize to carbon dioxide and water. So it was a consumption of 100 kgs of acetic acid per ton of product. Now, whenever we stopped the radical mechanism for polymerization and we had substantial quantity of dissolved oxygen, we know that the rate of reaction will be dependent on the concentration of paraxylene and concentration of dissolved oxygen. And since dissolved oxygen was much more, the catalyst quantity required we could reduce, and we could also reduce the temperature because that was getting compensated by huge quantity of dissolved oxygen. And therefore, at reduced temperature and reduced catalyst concentration, the consumption of acetic acid reduced from 100 kgs to 60 kgs to 50 kgs to now for less than 40 kgs, now closer to 30 kgs. Now this happened mainly because of innovation, but innovation is entirely based on the understanding of the basic chemistry, the fundamental chemistry and chemical engineering. Here I'm emphasizing the need for collaboration. We had to collaborate with excellent organic chemists and the chemical engineers in order to understand what was the controlling so that we are not getting the quality. Since the acetic acid consumption reduced and rate of oxidation enhanced, we could increase the capacity also by 50%, even at the reduced rate of consumption of acetic acid. And here is shown the schematically how the impeller designs, again, computational fluid dynamics, fundamentals of relationship between mass transfer and impeller design and power consumption. And this particular science of understanding fluid mechanics and its importance in the reactor design, we developed this as an expertise in the university. And we solved not only Indian problems, we solved problems from France, from Germany, from South America, from USA, from UK. And there was a lot of sponsored projects from everywhere. I'm going to give you one more example, that is froth flotation. This is a little different example from chemical industry. This is from metallurgy industry. We know that in froth flotation, the desired product from the raw material, it attaches the bubbles rise, and the desired product and bubbles, they accumulate at the top, what we call it as a froth, which is taken separately. the unwanted material is collected as gang material. Now in froth flotation, it is mandatory that the bubbles and particles, they should come in contact with each other. And specific level of turbulence is required for bringing these together. However, if the level of turbulence is higher than what is desired, the particles which are attached, they detach. And in classical mechanical machines of froth flotation with mechanical agitation, the turbulence is very intense in the vicinity of the impeller and it decays down, and near the wall it is 10 to 20 times less, at the bottom also it is less, at the top it is also less, and only in the 20 to 30% region of the mechanical cell the turbulence would be at the desired level. And again in the impeller vicinity it would be so intense that again the whatever was attached was getting detached. So there have been innovations in the world, and then the second innovation is Jemison cell, where we add a liquid and gas from the top, which is called a jet reactor. But what we did was a fluidization of solid particles, and we made the turbulence in the liquid phase the homogeneous and isotropic. That is, the intensity of turbulence was same in all the three directions. I would explain this in some other time, what exactly was innovation for making the turbulence isotropic and homogeneous. That is, at every location in the column, the turbulence was exactly the same, and the turbulence in all the three directions was also the same. And therefore, every point in the reactor had started becoming functional. What was the result? I'm explaining you. The y-axis is the fractional recovery of wanted material, whereas x-axis is the power consumption per unit volume. In the classical mechanical cell, we had to crush and grind the raw material, the natural ore, to about 200, 100 microns, sometimes 40 microns. Then only suspension would occur in the mechanical machine. And we know that the 7 to 10% of the world's energy is spent in crushing and grinding for winning the desired material from natural ores. What is that we have done? In the fluidized bed, we are anyway fluidizing the solid particles, bigger particles, for creating turbulence. And even if the particles are crushed to 1 mm size, they would also get suspended in the... So there was a huge saving in the energy. But where is the bigger saving? If you see the fractional recovery, the y-axis versus power consumption, and if you take power consumption of 5 kilowatt per ton, the mechanical cell would give 50% recovery, the improved machine will give 60%, whereas the flotation will give 85%. But this is a simple benefit. The most important benefit is, if you want, say, 70% recovery, then the mechanical machine would not give. And therefore, if you see metallurgy industry, then there are froth flotation machines in series. One would take recover 60%. The next one would recover 60% of the remaining 40%. The third one, 60% of the remaining 40%. And we need about 6 to 7 machines in series. And whenever there are mechanical machines, there are equivalent number of problems. But this fluidization machine, which has isotropic and homogeneous turbulence, which gives 90% recovery, no mechanical parts, and therefore this is implemented very extensively. The next partnership with the industry is chromatographic separation. We know chromatographic separation in the laboratory, where the columns are of sometimes micron size, sometimes millimeter size. And we use the principle of adsorption and desorption to separate the products from one from the another. But we need to do such chromatography on commercial scale and separate in not only kilograms, sometimes we need to separate in tons. And while this chromatography is to be done, the fluid mechanics becomes important, mainly because whenever we separate by distillation, we need 10, 20, 30 theoretical stages. But for adsorption, we need about 1,000 theoretical stages. So the the liquid solid contact, we need to make such a efficient so that we accommodate one theoretical stage in couple of particles, so that the height of the column, now it is not in millimeters, it is in terms of 80 centimeters, 1 meter, 2 meters diameter, and we need to accommodate 1,000 theoretical stages. And here the real innovation was required, that the solid liquid contact shall be uniform throughout the liquid, and there is no recirculation, there is no bypass, and the contact is uniform throughout. And therefore we innovated the distributed plate and the collector plate on the basis of fractal principle, which is shown schematically here. The liquid comes from the center, two separates into two fraction set, two further two, further two, further two. And therefore, if you take any one end point, even if it is closer to the center point or farthest from the center point, the liquid had to travel the same path. If you start from the center, then the black followed by green, followed by blue, followed by again green, followed by red, that is the farthest part. So if you take the closest point also, and this equal resistance on the basis of fractal principle, we could get 1,000 theoretical stages in about 1 meter height, and excellent liquid distribution and excellent. So this has been commercially exploited, and whenever it was being imported, again 25 crores, and we made it in 50 lakh rupees again. So if you want to enhance the competitiveness of industry throughout the world, then the competitiveness of the industry can be done only by these meaningful partnerships between university and industry. I'm going to give this example of synthesis of carbon nanotubes. Up till now, there was a collaboration with industry for getting the industrial. I have many, many more examples, but the summary is that if there is a meaningful collaboration between industry and university, those resulting innovations can make the industrial products which are competitive in the world. I told you our participation in the overall market is closer to 1%, but wherever we have participated in a certain sector of agrochemicals, we are selling 90%. In certain sectors of perfumery, the India is participating 65%. And this is possible, this wealth generation is possible only by innovations in the university with the help of the industry. And industry people are very wise, and their experience is very, very valuable. The next example is within atomic energy, where there was collaboration between different groups of atomic energy. The main contributor was, of course, the materials group. And there was a participation from the university. And the carbon nanotubes, I wanted for certain applications. And for that application, I received a quotation from USA for 1 gram, $60. For 1 gram, $60 for a certain quality. From China, which provides economically, again $10 per gram, 6 times less, but $10 means about 700 rupees per gram. And then we decided, later on I'm going to show how many uses are there for carbon nanotubes. And here a student from atomic energy registered in ICT developed this technology, but development occurred in BRC, so it is BRC technology. So with the help of a fluidized bed of carbon black in the range of 50 to 100 microns were fluidized by carbon-bearing compound like acetylene or methane. and there was catalyst embedded inside the carbon black. So the carbon source methane, this entire mechanism was understood by that student. I'm going to show the picture of that student little later, but he understood whether it is gas to emulsion mass transfer control, emulsion to solid surface reaction control, or from solid surface or internal diffusion control, or adsorption control, reaction control. And he studied, investigated that in greater detail, and it was finally found that below 800 degrees, it would be reaction control, and above 800 degrees, it is internal diffusion control. But anyway, the process was developed, and in about 2 hours reaction time, initially the process was developed for few grams. Then it was, the capacity was enhanced to 500 grams, and then to 2 kilograms. I'm going to go quickly regarding, but what is important here, that we could not enhance the rate of reaction since it was internal diffusion control. We know that the activation energy for diffusion is pretty poor. And if at the reaction temperature was 800 degrees, and even if 800 degrees is increased to 1200 degrees, any process which is internal diffusion control will make it 2 times, 3 times, 4 times at the maximum. But then when the catalyst was converted to nano catalyst, the nanoparticles, then the internal diffusion was completely eliminated. The 1200 degrees gave the reaction rate, and the reaction time came down from 2 hours to 2 seconds, which permitted to make the process continuous. So the carbon bearing compound comes from one end, that is left end. The furnace and the reactor is where the residence time is about 2-3 seconds, and then there is a method to separate the carbon nanotubes from whatever is either unreacted or products. So we improved the purpose conversion and the utilization of carbon bearing compound and the preparation required for the raw material and the purification method in such a way that the costs came down. And here I'm showing some slides of SEM, TEM, and Raman, etc., to show you that the quality was equivalent to whatever was offered by the USA or China. I'll go fast: single wall, double wall, multi-wall nanotubes. Here also you can count the number of walls, and here also the single, the HRTEM. Now it had to be scaled up, and the 0.5 kg we could make 500 grams in 100 mm reactor and 2 kgs in 200 mm, and it had to be further scaled up. But at that time, there was a need of the nation, and with this very senior management, the Honorable Chairman and the Director of BRC, they took a lot of not only interest, they encouraged the development of the composite for bulletproof jacket. And this was developed within BRC as an application of carbon nanotubes. So the same set of students, they synthesized the composite, and this was, I'll not go into the details, but it was a big news. And this could happen mainly because of within atomic energy, the chairman, the director, the group head, group director, the students, the scientists, all of them participated, and it was an excellent BARC technology. What is the Hindu said? Cheap and light BARC offers first indigenous bulletproof jacket. We were importing more than 100,000, 1,50,000. This cost of production, 15,000. Imported 11, 12 lakh kilos per bulletproof jacket. This is 6.5 kilograms. And further opportunities to bring down the cost. Now, I want to tell you, I told you several win-win situations. The industry sponsors, the government prospers. There are excellent, good opportunities for the jobs. And then the institutions sponsor, the prospers, the students prosper, and the teachers. So among these wins, I'm now going to add this one more win. The photograph whom you see from Atomic Energy from our own materials group, he received the Bhatnagar Prize of this year. So one more win. And the reactor which I showed you earlier, the flow reactor, that is for catalyst suspension, the same reactor could give the capacity, not only the yield improved, the capacity also improved, or for a given capacity, the reactor could be miniaturized, and that student has become expert in reactor miniaturization, and he has now developed several designs of micro reactors. And he, along with this student, Kinshuk Dasgupta, and that Amol Kulkarni, in engineering, there were 2 prizes, Bhatnagar prizes this year, and both the students who were from this group of innovation, one in the micro reactor and one in the bulletproof jacket, basically carbon nanotubes. Going further, of course, many newspapers covered this, but I want to emphasize here that is all the scientists are important, the administration, right from the senior management, all of them took the interest. And not only interest is minor, they gave lot of support and encouragement. But now for CNT, there are many other requirements. For instance, we know Fukushima accident, because pump stopped, the temperatures increased, and at that temperature, water reacted with the metal, hydrogen generated. Anyway, air was around, and explosion happened. And one idea being thought throughout the world, that if we keep carbon nanotubes as a storage for hydrogen, then this hydrogen will not be available for the reaction with oxygen. And for a typical reactor of 750 megawatt, 100 tons of carbon nanotubes are required. We have modified the reactor design to accommodate these 100 tons. So our nation has certain number of reactors. What I'm trying to say, the requirement of carbon nanotubes for making composites, our nation needs 600,000 bulletproof jackets. Then that carbon nanotubes are required. Then we did further innovations in catalytic hydrogenation, and when the noble metal catalysts are deposited on carbon nanotubes, the activity was found to increase in the range of 2 times to 10 times, and there is a business opportunity of another 10,000 crores. Polymer composites is yet another opportunity. Therefore, we wanted to scale this up further, and there is a technology development division in atomic energy which is available, and with their help we are trying to take this technology outside. But while doing that, the research is going on further, particularly the nitrogen doped, boron doped. The boron doped has enhanced the hydrogen storage. We are now going into graphenes and CNT fibers, and there are good successes in this direction as well. The most important point, the first column shows the worldwide manufacturers of carbon nanotubes. The last but one column shows the purity of carbon nanotubes, and last column shows what is the price they quote. The first company, 60% pure, 1,600 rupees. 90% pure, 5,200 rupees a gram. Let me repeat, 5,200 rupees a gram. I will not read the entire table, but some companies are also charging 1,82,000. Maybe their properties are superior. The technology that we are planning to transfer, if we make at 16 kgs per day and 1 ton per day, include the capital cost and operating cost and cost of raw material, 720 rupees per kilogram. 720 rupees per kilogram. Earlier slide, let me put it again. Last column shows 18,200 rupees a gram. What do we mean by prosperity of our nation? We should innovate in such a way that whatever is required by our nation, we should make us self-sufficient, and whatever is required by the world, we become competitive and hence become. Now this under Atmanirbhar, this is what is there in our BRC website. I have just downloaded, and this is a great success of BRC, I would say. And the testing has been done, and the technology is transferred to Midhanis, and there are discussions ongoing at high level regarding the transfer of technology. There where I interacted with naturally with reactor engineering group. At that time when I interacted 12 years ago, then the group director, Sinhaji, he welcomed me, and then he made Dr. A.K. Nayak, who was 40 years of age then, and he declared in the public that let me develop a collaboration between the young person. And then we found several problems which are listed here: hydrodynamics and the passive decay heat removal system, passive moderator. And we did simulations, we did pilot plants, and there was an invitation from the well-known publisher via the Wireless. And we published a book last year, Advances of Computational Fluid Dynamics in Nuclear Reactor Design and Safety Assessment. So this is yet another win. I was telling you win-win-win-win situations. I will stop today here, and I will give the next example where up till now it was university-industry partnership and possible innovations and win-win-win-win-win-win situations for our nation and making our nation prosperous by creating wealth for our nation. But the society requirement through the concept of silage of Dr. Kakodkar, that will be my next subject next time, how society gets benefited in a big way by innovations happening in the university. Thank you so much for today, and we will meet again. Bye.
Thank you, Professor Joshi, for an excellent and inspiring lecture as always. Your heart and your brain both work into your presentations. We can see the passion for the country's prosperity in your speech, and your ideas for innovations are so excellent. I'm sure a large number of people who are hearing the lecture would be inspired. So we look forward to your second lecture. Meanwhile, there are a few questions being asked by the participants. I hope you'll be able to take them. And one of them, which I've seen just now, is a person wants to know what is the recipe for converting the university into innovation centers. Because usually university is associated with education. Many people stop with education. So how to add value to the university to convert it to an innovation center?
I think first and foremost requirement is we should be open. This is the first requirement. Because of some reason, we develop expertise in certain area. Say, for example, I am teaching for last 50 years fluid mechanics and reactor design. I do research in fluid mechanics and reactor design, and I do industrial practice also, fluid mechanics and reactor design. So it is likely that the different people have different expertise. I'm going to answer your question in great detail in my next lecture, but I'll give you a short summary that whenever we have expertise, we should not sit in the university. We university people have a lot of vacations. If we should be able to find out what are the applications in our own specialization in industry and society. For example, our institution encourages faculty members to give in the vacation to spend extended periods in industry or in society. And our institution also creates an additional salary in addition to the regular salary. This is a small incentive, very, very small as compared to the final innovation. This is negligible. But the teachers go there, spend 2 months, 3 months, and they try to interact. Those who go to society, they try to understand the problems faced by the society. And I'm going to tell you next time at least 3-4 problems faced by the society and how they were solved and how that also generated huge wealth. The short answer to your problem is we should not remain in the university. We should travel. We should spend extended periods in the society and industry, try to understand the problems faced by them, and keep on finding the solutions. When you are young, then your answers may not be quickly accepted by either industry or society. But one day, one time, your answer is accepted once they test the success of your suggestion. Because I have passed through the same thing. I spent a lot of time when I was 27, and none of my ideas were accepted by industry. But I gave the ideas, and those ideas remained. And when they faced one problem and they implemented my idea, they got the solution to the problem. And then they understood the importance of such a partnership. Then the industry started coming, and now the present situation is there is a big queue of industrialists outside my door. By the way, my institution doesn't have doors. They can directly come inside. But I'm able to cater to only 10 problems at a time, more than that. But this trust and respect for each other, we need to create by spending extended periods and respect. There is lot of wisdom in society and industry. And as compared to that, we academicians have less wisdom. So we should learn wisdom from them and we should understand their problems. Don't remain in the institute and spend extended periods. Try to understand. There will be several answers to a single problem. Try to develop a mechanism to weigh each technology in terms of financial capital cost, operating cost, and how your answer is comparable in the world. Have some chip which is embedded in your brain of quickly calculating and the one thing which I have earlier said, I do not mind. There will be difficulties when you spend time in society and industry. And if you start complaining about difficulties, you are never going to innovate. You should never complain in life and go smilingly whenever you are spending any time. Then only you are going to make friends and you are going to develop trust. So spend time, develop, collect problems, get solutions. And innovation is unnecessarily a big word. There is nothing a big content in that. We keep on finding solutions. One of them is economically attractive. Implement it. When it is implemented, it is called innovation. It is that simple. Yeah.
Thank you. Another question was, what can be the mechanism by which an industry which faces a particular technical problem poses it to a university? Is there a formal mechanism somewhere, like posting some question to some particular cell in the university or on the portal of a university? What way can the industry bring its problem to the university?
At present, it does not exist. Not even in minor form, it doesn't exist. Maybe for the earlier question and this question also, I'll prepare 3-4 special slides next time. And one quicker way is every university has some specializations because of some reasons. And they in their website, they should, I think, publicize what is the expertise available. I think I'll give the very, very detailed answer how to nurture and maintain the university industry, how to begin and how to do that. I like this subject very much, and I'll cover that nicely.
And one of the participants has asked a question about titanium extraction. You have mentioned it as one of the challenges in the beginning where innovation can make a lot of difference. You have had any experience on that or suggestions?
There is one innovator. I passed my chemical engineering in 71, and my colleague who is innovator, he passed in 1949 when I was born, but we are working together. He is industrialist. He never bought any technology from outside. He's an excellent chemist, excellent chemical engineer, excellent entrepreneur, and gives donations to a lot of foundations and for the society. His name is Dr. Ghada. He took this problem on his head, and I'm happy and fortunate to be associated with him. And the technology that we are developing is from the sand, which contains titanium, aluminum, and iron. We are first of all smelting, and first of all getting all the silicates of that. And oxides are converted to silicates by reducing with carbon monoxide and hydrogen. These silicates are carbochlorinated to get titanium tetrachloride, aluminum trichloride, and FeCl2. The boiling points are quite different from each other. These are separated by distillation, and then individual majority of iron, which is totally carbon free, we get in the smelting process. Small quantity gets carried forward, and titanium tetrachloride and aluminum chloride, these are electrolyzed to get the titanium. So what we are keeping the aim, aluminum cost of production is about 150 rupees a kilogram. The titanium is being sold at 2,500 rupees a kilogram. Our objective is to make titanium at the cost of aluminum. And I'm sure we will go in, and that is called innovation. I'm sure we will go in that direction. We have already proven that for making 1 kilogram of aluminum, about 13.5 kilowatt hours are required in electrolysis. We have been able to reduce to less than 10 kilowatts. This is how the benefit doesn't come from one innovation. You have to put 5 innovations, 10 innovations together to give the overall effect so that the titanium will be manufactured. Maybe this example I'll also explain next time. I like that example.
I have a question from my side. In the beginning, you showed very interesting examples of the yield or production capacity in our country for our area as compared to other countries. And the most striking in that example was of tomato. Subsequently, in the talk, you talked about industrial related problems, more related to fluid mechanics, thermal hydraulics, or production of materials, etc. Now, if you go back to that example of tomato, it is not, we have seen that you also mentioned that industry had some complaints, then academics has complaints, and common person has complaints, some complaints. So what comes in the way of our increasing the yield of tomato, which will be making very big impact for us?
Our nation is facing dual problem. One is a reduction in fertility of land, and another problem is what to do with solid waste after the major crop is one. And our country has more than 400 million tons of such agricultural waste. And now the November is coming up, and the pollution will start because it is open burning of the residue is done. And you will start getting the news in Delhi area. Actually, in Delhi area, pollution is publicized, but this agricultural waste is burned throughout the country. Now, this problem of the utilization of agricultural waste and improving the productivity of land or making the unfertile land fertile with the help of waste, I will cover in great detail in my lecture, next lecture, where I'm going to cover basically development of the knowledge and the utilization of the knowledge in the village sector, the concept of silage of Dr. Kakodkar. And here, this will be one of the most important examples that make our land fertile and also simultaneously solve the problem of agricultural solid waste. So I will do it together. And not only we have postulated, but we have taken certain crops and increased the productivity back to whatever proven in the world. That possibility is there, which I will cover next time.
I think we will stop here and thank Professor J.B. Joshi profusely for not only his excellent lecture, but also for expressing so much interest in taking science to society and trying to inspire more and more to join his concept. I'm sure that the next lecture will be equally inspiring, and we are keenly waiting for the lecture. We will announce once the date is decided to all the participants who have joined today and even others. So we will look forward to your next lecture, sir. Thank you very much. And also I thank a large number of people who have joined both on WebEx and YouTube. And I'm sure that number of you would have got inspired by listening to Professor Joshi. In particular, I want to thank Dr. Anil Kakodkar and Dr. Chidambaram. You are joining us for these webinar programs. Helps us to encourage ourselves to organize more and more such webinars. So thank you for joining. Then we will meet again after some time. And as I mentioned, these lectures are going to be available on YouTube, because these are being streamed through YouTube. There's a HBNI webinar channel in which you can find the recording of this lecture after some time, perhaps. Thank you very much for joining.